We want to find where the function h of x is increasing and where the function h of x is decreasing on the interval from negative infinity to positive infinity. Let's go ahead and do that. The first step we need to do is to find the critical values. That requires me to take a derivative. In this case, that is 3x squared minus 10x plus 7. That is always going to exist no matter what x value you plug in, but there are x values which the derivative could be 0. So set the derivative equal to 0 and solve. I believe this factors. Let me check that out. If this factors, it would be 3x plus a number times 1x plus another number. Those two numbers, the m and the n, would have to multiply to give me -7. And then when I multiplied to give me my middle term, they'd have to add up to -10. So in order to multiply to give me a +7, I'd either have to use a +7 and a +1, but this would give me a +10 in the middle, or I'd have to use a -7 and a -1. And if you multiply these out, you would get a -10 in the middle. So this quadratic factors into 3x minus 7 times x minus 1. The zero factor property tells me that either the 3x minus 7 could be 0, or the x minus 1 could be 0. Solving for x, this means x could be 7/3, or x could be 1. Obviously, both of these critical values are in the interval from negative infinity to infinity. 7/3 is about 2.33. It's 2.33 repeating, or 2 1/3. So 1 is the smaller number of these two. That means my subinterval, or my subintervals, are going to go from negative infinity up to the lowest critical value. Lowest critical value is 1. Then I'm going to go from 1 to my next highest critical value. My next highest critical value is 7/3. And then I'm going to go from that 7/3 all the way up. If I had another critical value, I'd go up to it. But since I don't, I go to the end of my interval, which is infinity. We have 3 subintervals here. Let's check on each one whether or not we have positive or negative derivatives in each subinterval. Let's start with the negative infinity to 1. We need to plug in some number in this subinterval. The number 0 works really nicely with polynomials. If I plug in 0 into the derivative, I get out a 7. The important thing there is that the derivative is positive. So that means the original function, h of x, is increasing on the interval from negative infinity up to 1. Let's look at the next subinterval from 1 to 7/3. We plug in to the derivative some number between 1 and 7/3. I'm going to use 2 Obviously, you can make this 1.5, you can make this 1.75, you can make it any number between there, but for sake of ease, do the easiest thing you can. So 2 is a pretty easy number to plug in. We'd take 3 times 2 squared minus 10 times 2 plus 7. That gives me out a -1, which is important because it's negative. Therefore, the function h of x is decreasing on the interval from 1 to 7/3. My last sub-interval is from 7/3 to infinity. Let's plug in some number that's beyond 7/3. I guess we can make this an 8. You can make it whatever you'd like. Any number that's bigger than 2.33 repeating would have worked. When you plug in an 8, remember you're plugging that into the derivative, this 3x squared minus 10x plus 7. When I did that, I ended up with 119, which is positive. And that means my original function, my h of x, is increasing on the interval from 7/3 to positive infinity. So you can see that the derivative is telling me some sort of properties of the original function. And that's how this all works. Hopefully you came up with all of these, that h of x is increasing from -infinity to 1, h of x is decreasing from 1 to 7/3, and then h of x is again increasing from 7/3 to positive infinity. And just to remind you again, in this case, we swap from positive to negative to positive again, or in other words, from increasing to decreasing to increasing. There are some functions that would go increasing twice in a row or decreasing twice in a row.